So in this video we're going to have a look at some titration curves. And a titration curve is a graphical way of showing what happens when you react an acid with a base and how much base you've got to add in order for the acid to be neutralized. So what we're going to do is we're going to start with the first one, which is a strong acid versus a strong base. An example of a strong acid, hydrochloric acid or sulfuric acid, but we normally use hydrochloric acid against the strong base, which is NaOH. And what we're going to do is we're going to look at our graph and we're going to add some base on the x-axis and the pH is going to be calculated on the y-axis. So if we're starting here at 0 centimeters cubed, so when there is 0 centimeters cubed of base added, that means we just have the acid, the strong acid. And the strong acid has a pH of around 1, we'll say. And as you start adding the base, the pH of the acid will stay pretty much the same. And then as we start adding the base, it will become less acidic. So the graph then starts to rise. And it rises gently. But generally, as we get around towards 25 centimeters cubed, what happens is we're now suddenly at a pH of in here around, maybe 2.6 or 2.7, something like that. But all of a sudden at 25 cm cubed, there is a sudden change in the pH. The pH of the solution that we've got with one drop suddenly neutralizes, and the pH jumps from 2.7 and can jump up as high as maybe 10 or 11. That's represented by a long straight vertical line, like this. If we continue to add the base, then it gets more basic. And then it eventually, as we add more base, it eventually plateaus out and doesn't get any more basic. So these are the 2 points that we're interested in. It suddenly jumps from 2.7 up to about maybe 10, 10.1, something like that. When we have a strong acid and a strong base that shows this, then what we've got to try and do is try and get an indicator that will work between these ranges. Now we've already seen in previous examples that methyl orange will work between the range 3 to 5. So that means methyl orange would work in here. So we could use methyl orange as an indicator because that will detect it. Now it works between 3 to 5. Litmus would also work here because litmus works in the range 5 to 8. And finally phenolphthalein. Phenolphthalein would also work here because that works in the ranges 8 to 10. So for a strong acid and a strong base, any one of these indicators would work. You pick your indicator based on this middle piece here, which is called your equivalence points. Let's have a look at the next one. So here's our next one. And this time we're going to be doing a strong acid, again HCl, against this time a weak base, ammonia. So the same thing applies here. If you're starting with your acid, you're at a pH of 1. You haven't added any base yet. So the same thing happens as you start adding your base. You're going to start increasing. And the pH then is going to slowly start increasing. Again, up until generally around 25 centimeters cubed. And then once the base kicks in, this is the point at which it jumps. But the jump is much smaller this time. So when you're dealing with a weak base, because it's a weak base, it doesn't jump as high. So what we find when we're reacting these two together is it goes as far as about 7, and then it starts to taper off a little bit less, all the way across. So here now we have a range of about a pH of 7, and we have a pH, again, in around 3. So that's the jump. So now what we do is we go look to our indicators and we see which indicators are suitable. The only indicator that's suitable here would be methyl orange. Methyl orange is the only one that would be able to detect this because methyl orange operates in the 3 to 5 range. We can't use phenolphthalein. Phenolphthalein is colorless up to a pH of 8 and will only change color when it goes to pH of 10. So phenolphthalein wouldn't have any color change in a strong acid versus a weak base. Moving on to the next one then. So on the third one, we're going to have a weak acid against a strong base. So a weak acid here would be ethanoic acid, which is CH3COOH. That's a weak acid. And then we also titrate against a strong base, which is NaOH. So what would the pH of ethanoic acid be? So in this case, we're starting generally in around 3 this time, because it's a weaker acid than the ones we've seen before. And of course, as you add the base then, it starts getting slightly more basic. And where does it change? Well, it starts to change in around 6 to 7. So in around here, we're going to hit a pH of around 6.5 or 7. And what it's going to do is then it jumps up and it stops around 10, and then it levels off. This is around a pH of 10. So looking at these 2 points, now we've got to see which indicator would do the trick here. So the indicator that would do the trick here, the only one that would work, would be phenolphthalein. The reason why is phenolphthalein works between 8 and 10. Litmus wouldn't be any good here because it only works between 5 and 8. So we wouldn't catch the end of this. So phenolphthalein works perfect for us there. So the final titration curve that you have to look at is the weak acid versus the weak base. So again, if we're starting with a weak acid, we're looking at a weak acid starting in around a pH of 3. So when it starts as a pH of 3, so it starts to rise, and it rises fairly gently until it gets to around 25 centimeters cubed, and there's a bit of a change, but to be honest, it starts to level out very, very quick. Now, as you can see here, there isn't much of a direct change. So because there's not much of a direct change, there's actually no indicator that we can use to figure this out. You need a steep curve, so you need something that goes up in a straight line in order for an indicator to be able to detect the color change. Because the change here is gradual, there's no indicator that we can use when titrating a weak acid against a weak base. That pretty much finishes it for your titration curves. You don't need to know any other combinations.